We will now consider some examples that apply Green's theorem. In each of these examples, we're going to look at an integral of f dot dr and we're going to evaluate that integral by instead considering the double integral over the region R that's enclosed by that curve C of dq dx minus dp dy dA. So for our first example, we're going to integrate around a curve f dot dr, where f is the vector field y squared and 2x minus 3y, and c is the circle x squared plus y squared is equal to 9. So here, c is that circle of radius 3. We're going to give it a positive orientation. And then what we would like to do is instead consider an integral over the region enclosed by C. We'll call that region R, and perform the appropriate double integral. So here, if we were to do this integral around the circle, we would have to parameterize the circle. We would substitute that parameterization into the vector field. We would also have to take the derivative of the parameterization to find dr. This would be a long and complicated process. But instead, I'm going to look at f being the vector field pq, and I'm going to notice that dq dx in this case is going to equal 2, and dp dy is going to equal 2y. So instead of doing this line integral of f dot dr, I'm instead going to consider the integral over that circular region R of 2 minus 2y, so that's dq dx minus dp dy dA. And so what's in the integrand is much simpler in this case, because taking derivatives of p and q has made this function that I need to integrate more simple. Now I want to integrate over a circular region, so the most natural thing to do here is to convert this to polar coordinates. So here I want to integrate from 0 to 2 pi in theta, and then I'm going to integrate from 0 to 3 in r. That circular region is much better described using polar coordinates. So then what I need to integrate is then 2 minus, and then y is going to be 2r cos sine theta. Okay, so 2y is 2r sine theta. And then dA is going to be r dr d theta. So first I want to integrate, and I'm going to integrate with respect to r first. So I'm going to get the integral from 0 to 2 pi. And when I integrate 2r, so the antiderivative 2r is going to be r squared. And then when I integrate 2r squared, remembering that I'm multiplying everything by that r, I'm going to get 2/3 r cubed sine theta, and I'm going to evaluate that between 0 and 3. So in this case, I get the integral from 0 to 2 pi. And then I'm going to have 9 minus 2/3 times 27. So that is going to be 18 sine theta d theta. Now, integrating that with respect to theta, I'm going to get 9 theta plus 18 cosine theta evaluated between 0 and 2 pi. So 9 theta, when I evaluate that at 2 pi, is going to give me 18 pi. And then when I evaluate 9 theta at 0, I'm going to get 0. 18 cosine of 2 pi is going to give me 18. And then 18 cosine of 0 is also going to give me 18. And so those 18s will subtract, become 0. So I'm really just left with just 18 pi here. And so this, even though I had to convert to polar coordinates, is a much simpler integral to do than to parameterize the curve C and then do the integral of f dot dr. Okay, let's do one more example. So I want to evaluate the line integral. And this integral is written as an integral of p dx plus q dy. And so I want to perform that integral where C is the positively oriented boundary of the region R, bounded above by y equals x and below by y equals x squared minus 2x. So I'm going to first just plot y equals x. So that will be part of my curve. It'll be going in a counterclockwise direction. And then I want to plot the region below, y equals x squared minus 2x. So that includes the point 0, 0. I'm going to, at 1, I get the point -1. At 2, I get the point 0. And then finally, at x equals 3, I get the point 3. And so this is a parabola that intersects with the line y equals x at x equals 3. So we see there are intersections there at the point 3, 3 and the point 0, 0. So I want to do this integral. I want to compute the line integral by using Green's theorem. So I'm going to instead consider the region that's enclosed by these two curves. So that region will be R. So I'm going to apply Green's theorem here to say that the integral, okay, of 3xy dx minus 2x squared dy around that closed curve, okay, is going to be a double integral over the region R. We can describe that region as y going from x squared minus 2x to x. So here, remember we have y equals x squared minus 2x on the bottom, y equals x on the top there. And then x, you can see, goes from 0 to 3. So we're going to integrate this dy dx. And then what we want to do is integrate dq dx. So let's see here that dq dx, in this case, is going to be 4x. And then dp dy is in fact going to be 3x. So what I'm going to integrate is 4x minus 3x. So in fact, what I need to integrate here is x. Well, that's going to be the integral from 0 to 3 of x is a constant, so I can just pull that out. And so if I integrate 1 from x squared minus 2x to x, that in fact is going to be just x minus x squared minus 2x. And then I'm just going to want to simplify this just a little bit. So this will be the integral from 0 to 3. I'm going to notice that I have x times a minus x squared. That's going to give me a minus x cubed. And then I'm going to have a plus 2x plus x. So that's a 3x times x. So that's a plus 3x squared. So I'm going to integrate that dx. And finding antiderivatives, I will get negative 1/4 x to the 4th plus x cubed evaluated between 0 and 3. So that is negative 81/4 plus 27. And again, minus 0. And if we add those up, we will get 27/4. And so here again, we've taken what would have been a fairly complicated line integral in which we would have had to parameterize two different curves and then evaluate the vector fields at those two different curves and perform those two different integrals. And we've combined this into one integral. It's a double integral over a fairly simple function. The function that we integrated was x.